Welcome, friends. Now we enter the section of Calc 3 where we really are in multivariate calculus, which is essentially what Calc 3 is. So we're going to begin discussing partial derivatives. And the idea of a partial derivative, essentially what we do is we're going to take all but one of the independent variables and make those constant. So the idea here is that we are dealing with multivariate or multiple variable functions. So we've got an x and a y that we are maybe needing to differentiate with respect to. So we're going to pick the variable which we're going to differentiate with respect to, and we're going to hold the other variables constant. All right, so when we're differentiating with respect to only one of the multivariables, we get a partial derivative. And since if we are dealing with some surface, suppose we've got some surface here or a piece of a surface that we're considering, and there's a point on that surface. There's not just one direction that we can approach on that surface to get that point. Or to reach that point. There are infinite direction, right? And since a point can be approached from multiple directions, differentiability, being able to differentiate the function, requires more than just the existence of partial derivatives. Differentiable functions of several variables, these behave very similarly to differentiating a single variable function. So I'm going to pull in the definition and we'll talk about it. So here's the definition. The partial derivative for a multivariate function with respect to x at some point, that would be given, these would be numerals, x naught, y naught, is partial f over partial f of partial x, evaluated at that point. And so if you look at this definition we see here, this looks pretty similar to our formal definition, our limit definition of a derivative, which says that f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. So it's the same definition. We just kind of have this new notation. So we'll talk about how to use this and solve these problems here in a second. But what I do want you to notice for this example is that since we're differentiating with respect to x, you notice that plus h is attached to x, not y. So we can also take the partial derivative of a function with respect to y, and that definition looks very similar, just a little bit different. So here you can see I've pulled in this second definition. And the second definition, we're dealing with respect to the y variable. So notice that plus h is on whatever that y value is for my ordered pair. So before we do an example, we're going to talk a little bit more about the notation here for partial derivatives. So you might see this, which I've circled, partial of f with respect to x at some point. So let's talk about that notation. If I had partial of f with respect to x evaluated at x naught, y naught, some other ways I could write that would be d dx, take the derivative with respect to x of this function of several variables evaluated when x equals x naught. So we've got a value here. We could also say this is the same as writing partial f, partial x, x naught, y naught. We could say this function differentiated with respect to x, x naught, y naught. Or recall, you guys, that sometimes we say z is a function of xy. So we could say partial of z with respect to x. So these are just all different notations. They all mean the same thing. They are all referring to finding the derivative at a point. So we have values for x naught and y naught. As a note, you might see just partial f, partial x, or the derivative of f with respect to x, partial z, partial x. So these notations don't have a point there. They're not the derivative at the point. That's the general derivative or the general partial derivative. So this partial derivative that we've talked about here, partial derivative, partial f with respect to x at that ordered pair x naught, y naught, this gives the rate of change of f with respect to x when y is held at some fixed values. So when the y values, we make those a constant. So when we're differentiating with respect to x, we're going to treat those y values as a constant. All right? So I'm going to try and sketch this for us, because I think when we sketch it, it makes a little more sense than if I just pull in the picture. So we've got our right-hand coordinate system, x, y, and z, and we have this surface that we are considering. So this is some curved surface here, and I'm going to finish drawing that little bottom piece in as we get there. So we've got some curved surface that might connect like that, but for matters of perspective, I'm not going to draw that yet. And so there might be a point somewhere in space on this surface. So I'm going to draw that point. I'm going to come out here and say we have this x naught, y naught point. And we can think about this as like a cube. That's not very straight. You can think about this as a cube, and that point is up in space on the surface of that cube. So here's my point on the surface. Point, we'll call that point P. And essentially, if I consider that these lines, and that should be dotted, extending out here, that's going to help me draw it nicer. So we might have some curve that we've cut a piece of this out here. So I'm going to kind of draw this in my perspective like that, and then like this. So this is a slice here out of my surface. So at that point P, we have several curves. So one thing is I have this curve right here, which runs along the surface in that YZ plane. So that curve, Z equals F, I'm not going to have enough space with that error, F of x naught, comma, y. So y and z are my variables. And that is in the plane where x equals x naught. So similarly, I have this curve running through here, and we might call this curve z equals f of x, comma, y naught. So this is in that plane where y is equal to y naught. It's in the zx plane, this curve, or it's parallel, I should say, to the zx plane. So what this partial derivative does, the partial derivative with respect to x for this function gives us this tangent line that runs in this direction. So it's the tangent line slope right at that point on the curve or on the surface in space, but on that curve Z being a function of X, that gives us the tangent line. So this is the partial with respect to X of X naught, Y naught. Whereas if I look along the other curve, this purple curve here, that's going to give me a tangent, and that might not be the best tangent, but I hope you guys get what I'm doing. That's the tangent line slope. That's what the partial gives us. And that's the tangent with respect to y. So of that point, x naught, y naught. So you'll look here, x naught, we turn that into a number, the constant. That gives us the partial with respect to y. Whereas on this curve, we turn y into a constant. We're taking the partial with respect to x. All right, so I'm going to pull in the picture now that I've drawn that. And it's the same, they've just kind of cut that plane out a little bit differently. But I hope this kind of helps all of this make sense. So we have a point, and when I find that partial with respect to y, it's falling in some x naught plane because x naught has been made constant. Similarly, the partial with respect to x, that is lying in the y naught plane, y equals y naught. Okay? So there are a ton of different tangent lines on this surface that I could draw through that point, but we're looking for ones in specific planes. All right, so I hope that helps you kind of understand what the partial derivative is. The partial derivative is giving us a slope in a specific direction. All right, so I'm going to stop this video here, but in the next video, we're going to do some examples where we find partial derivatives.